Path analysis DA demo. Okay, if you've started the DA, I hope this will be more familiar. If you haven't, you're getting a little bit of a head start. So the data that we're looking at comes from an article from 2020 by Mustafa and colleagues on job satisfaction and turnover intentions, and specifically the roles of features of one's job. So job autonomy, job variety, and work passion. And it was specifically looking at intentions, both job satisfaction and intentions to quit in family, small to medium-sized businesses. So looking at essentially the impact of job functionality or job structure during COVID times in family-run small businesses. So this data comes from this article, which you can read in its entirety if you're interested. Here are the measures. So work passion, how much passion individuals have for their work, job satisfaction, which is the global attitude towards one's job, turnover intentions, intention to turn over, intention to leave the organization, job autonomy, so how much autonomy you have in your tasks, and job variety, how much variety or different types of tasks do you get to do. And for those of you who are in org, you've heard about the job characteristics model. Both job variety and job autonomy are generally two drivers of both job satisfaction and engagement. So it's features, how features of your job impact your satisfaction. So this is the model that was presented to you in the DA. So for those, I'm assuming everyone has looked at it, but let's just pretend for a second that that's not true. And essentially what the DA asks you to do is it says, hey, this is your starting model. I want you to go ahead and specify and estimate this model. And then I want you to estimate a different path model of your choosing. So you'll notice one big thing about this model is it doesn't include turnover intentions, right? So your first model that you're running doesn't have turnover in it. You might opt to put turnover in your second model. And it also tells you how you respecify. It's totally up to you. So you know what these things mean. So you could just use your brain logically to think like, how do I want to reorder or restructure these variables? You can look at the actual results of this model and see if it guides you in some way to respecify, or you can run mod indices if you want and get the data-driven, R-driven suggestions for respecification as long as you say that you used it. So what I did today in prep for today is I ran this model, just like exactly like you will, and then I respecified one model. Ideally, don't respecify the same model we look at today. There's a lot of combinations, but if you want to, it's fine because I'm not posting it. So all right, so this is the first model. We're gonna specify this as a path model, but does anybody, there's something very interesting about this. TAs, I wanna put this in the improvement doc for next year. Anybody notice something interesting about this? Do we need path analysis? No, we don't. Why? It's not that there's no mediation. It doesn't have two outcomes, right? This is a regression, right? We just regress job variety, job autonomy, work passion, and then the two interaction terms onto job satisfaction. Not needed for path analysis, not needed. However, path analysis is just multiple regression equations put together. So we can still run this in the same Lavon code we've been practicing for path analysis. We're just gonna have one equation instead of multiple. So that's what we're gonna do, because then if I specify something else that has two outcomes or three outcomes, then I'm gonna need that path analysis. So I don't want people using JMV to run a single regression on this. Do it in path analysis. All right, this is our theoretical model. This is not what our statistical model looks like. Why? Because we can't regress something onto a line. Right? So the first thing that we're going to need to do is actually create. So I'm going to go back and forth between demo and slides. So let's read in the data. Very simple data set. Looks like this. I converted all the column names to lower so that I don't need to see them again. We're going to go ahead and run descriptives of our data. Job variety, very lovely. Everything looks like a very lovely normal distribution, actually. Here are our descriptives. So we've got a 1 to, oh, that's the participant, 1 to 7 scales for all of our variables, right? So everything was measured on 1 to 7, and we've got the minimum and the maximum values present in the data set. So we have a good range of values, right? We're checking to make sure we actually have some degree of variance to predict in job satisfaction, right? And if we look at job satisfaction, we've got a standard deviation of 1.1. That's decent for a 1 to 7 scale, right? Not everybody has the same level of job satisfaction. So we can go ahead and try to explain as much variance in that as we can. Next thing we're going to do is run our correlation table. Notice I took out column 1 because that's the ID column. Okay. So we've got a negative relationship between turnover intentions and job satisfaction, a positive relationship between autonomy and work passion and job satisfaction. So this is another place where you can get information about how you might want to respecify your model, right? This is giving you how each of the pairwise comparisons are related to each other. So this would be another place to go if you're like, how might I respecify my structural model? Now we need to look at our assumptions before we ever start playing with model specification. So these are all regression equations, right? Path analysis is just a bunch of regressions put together. So we're still in the box of general linear model, which means all of the assumptions for the general linear model hold. So what are they? Linearity. So let's start there. So we have a scatter plot here between job variety, job autonomy, work passion, predicting job satisfaction to make sure there's actually linear relationships between each of our predictors and our outcome. Looks pretty good, looks pretty good, looks pretty good. All positive relationships, but all generally linear. So we've got linearity. What's next? Come on, it's been a whole module. You can say it. Homoscedasticity. Good. Homoscedasticity and multivariate normality. So in order to do that, I need to create a saturated model, right? A model that predicts job satisfaction from my 3 predictors. And then I'm going to go ahead and run homoscedasticity first. And let's take a look, right? Reminder that what we're doing is comparing predictor values down at the bottom, so fitted values of our model, and how much error we have. We don't care whether there's a lot of error or a little error from this picture, though it gives us a hint on model fit, right? But what we care is that that error is constant. Is it constant? Right. Is it constant? Pretty much. I mean, it looks, there's not a huge, it's not like I can very clearly say, ooh, for high values of the predictor, the model doesn't fit, and for low values it does, right? But we can confirm that with our variance test. So that's looking whether there's a relationship, a significant relationship between our fitted values and the amount of error. We want it to be what? Non-significant, right? We don't want there to be a relationship. And yay, chi-square, degrees of freedom 1, 0.22, p-value 0.641. No significant relationship between fitted values and amount of error in the model. Meaning the data is homoscedastic, right? Not heteroscedastic. And functionally, that means that the predictive power of our model works equally well, regardless of what people's predictor levels are. Okay? Questions so far? Get them out while you can. You're like, no, this is repeat. We do this. Good. Now let's check out multivariate normality. That's beautiful. Never seen a QQ plot that looks like that. That's pretty nice, pretty straight. And again, p-value, no significant difference, right? We're retaining the null. The p is greater than 0.05. And the null is there's no difference between your data and perfectly normal data. So in this case, the data are multivariate normal. That's pretty sweet. Never happens. We've satisfied all assumptions. I literally don't think that's ever happened. Now, if we hadn't, what is this impact in our model specification and estimation? This has an impact on one very specific thing when we're running path models or SEM models. Yes, but that is what? So bootstrapping is a solution, right? The word I'm looking for is estimator. Right? We choose how we're going to estimate parameters, and the features of our data dictate what estimator is appropriate. If all of our data are normal and homoscedastic, default maximum likelihood is A, as long as we don't have a what? What type of relationship, if we have this in our model, could we not use ML for? Mediation, right? We'd actually still be using ML, but we'd be using ML with bootstrapping. So maximum likelihood, our data meet all of our assumptions, that's fine. If our data were not normal or were heteroscedastic, what adjustment would you make to the estimator? Robust maximum likelihood, right? It says, hey, I know your data is a little wonky. I'm going to adjust your standard errors to account for that. So robust maximum likelihood. If I've got ordinal variables, so counts, right? Categorical variables in my data, what am I going to use? Do you remember? This one's trickier. We only did it once. We're going to use weighted least squares. So far 3. Totally normal continuous data, maximum likelihood. Non-normal or heteroscedastic continuous data, robust maximum likelihood. Got any ordinal categorical variables in there? Tell R what they are and use weighted least squares. Bootstrapping is not actually an estimation technique. It's a technique we apply over the estimator, right? We're gonna add in bootstrapping if what? If we have a mediation. Cool? Does that help clarify the estimation piece? There's more, but we're only gonna talk about those three. Yeah. You can't. If you try to do that in your code, it won't let you. Because what is bootstrapping doing? It's creating your own standard error, right? So you can't both ask for the theoretical adjusted one and create your own, right? So when you use bootstrapping, it's defaulting to just normal bootstrapping with maximum likelihood. Yeah, that's a good clarification, right? If you're using maximum likelihood or robust maximum likelihood, that is using predetermined T and Z distributions. It's just giving you a little leeway if you use robust. If you're bootstrapping, you're not doing theoretical distributions, right? They are what? Not theoretical, but empirical, right? Good. Practice for the quiz today, right? Good. So if you're doing that, R doesn't have default standard errors to adjust. Good question. Any other questions so far? We're just through assumptions. The next thing I'm going to do let's go back to the slide now. So this is my theoretical model, but this is not my statistical model. This is my statistical model, right? Boo, it's just a regression, but that's fine. We can run it as path. All right, so this is our model. We've got very simple multiple regression, 5 predictors predicting job satisfaction, right? So that means we have to do what before we can run this? We're missing something in our data.
Centering predictors.
Right? We don't have job variety times work passion in our data set. Look at our data set. Oops. Right? We just have our predictors and our outcome, right? So we need to create our moderators. What do we usually do before we create moderators in moderation?
Center the data.
Now, tricky thing. In this example, we could center our data no problem, right? Because we have clear predictors and we have an outcome. But what happens if we're working with a more complicated path model where we have things that are serving as both predictors and outcomes, right? Well, then what do we center? Tricky, right? So one way to get around that, which I usually do in path analysis, is rather than worrying about centering anything, I standardize all of my data. That accomplishes the same thing as centering, right? Because then every person's score is being expressed relative to the mean in z-scores, right? So when I say I standardize, I convert everybody's continuous scores into z-scores, right? That we don't need to do that for this particular model. We could just center, but because I know I'm going to run other models where I mess with stuff a little more, might as well just standardize my variables. So I'm going to standardize my variables and I'm going to create my moderator terms. Here in line 84, I'm creating a new data set, STD for standardize. I'm going to start with the original data set and then I'm going to mutate across, meaning I'm manipulating columns 2 through 6 and I'm scaling them. So this is standardizing your data. What does centering do? Subtract the mean from every data point, right? What does standardizing do?
Also provide the spread variance.
Good. Standardizing also does that, right? Remember how to get a z-score? X minus the mean over standard deviation, right? So see how it accomplishes exactly what centering does, but also puts it in standardized units. You never need to center and standardize. They accomplish the same thing. So we're going to standardize our data, and then we're going to create 2 moderator terms. The first I'm going to call JVUP, so job variety work passion mod. And the next one I'm going to call JA, job autonomy work passion mod. Here they are. So now everything is expressed as a z-score. If I were to highlight this number right here, person number 3 has a JV, a job variety score of 1.60. What does that mean?
More job variety than the other by 0.6.
1.6, right? So 0, what's a z-score of 0?
Mean.
The mean, right? So a z-score of 1.6 means this person's job variety is 1.6 standard deviations above the mean. Okay, just a little A review there. All right, so now I've created my moderator terms and I'm ready to fit this model. right? I'm ready to specify and estimate parameters from this model. Before I do that, let's take a walk down degrees of freedom lane with this model. Oh, these didn't say, that's fine. You can ignore those boxes for a second. So here's our model. And remember that degrees of freedom for our model is the amount of unique pieces of information that we have minus the number of parameters being estimated. In path analysis and in regression, what are the unique pieces of information I'm referring to? It's not number of observations of people. What is it? Kayla, the boxes. What are those? This one is what? Good. The variance of each of our variables. We have that in our data. That's known information. What else do we have? Not variance, but covariance, right? Remember that underneath the hood, regression is always just how do things move together, covariance, relative to how they move on their own, variance. So the known information we have is I can run a correlation table on all this data, right? And I'm gonna get all the correlations, but those are standardized. I could ask from unstandardized and I'd get all the covariance. So how does work passion move with job satisfaction? How does work passion move with job variety? How does this moderator variable move with job autonomy, right? And then I get the variance of each of those. So the known information that we have looks like this, okay? It's just the variance on the diagonal and the covariance on the off diagonal. Again, just a correlation matrix, but in raw units. Okay, we can count them, or we can use the simplified formula here, which is k squared plus k over 2. How many k do we have?
5.
No, 6, right? We have 6 variables. It's not just predictors, it's all variables, right? Anything that goes into making the matrix is a k. So we've got our 5 predictors and job satisfaction. So if we take 6 times 6 squared, add another 6 and divide by 2, what do we get? 21. If I were to count all the boxes that have words in them right now, I would get 21, right? The formula is just a shortcut. So we have 21 known pieces of information. Dang, that sounds like a lot. We should be fine with degrees of freedom, right? JJ's like, nope. So now let's figure out what we're actually estimating. What does it mean when I say what we're estimating? Can somebody explain that in like non-stats language? Because I use it a lot, but I want to make sure we understand. Other than estimate, yeah, figure out. Yeah, it's any relationship we're trying to figure out in the population, right? So anything that we say, hey, R, give us a number back for this that represents this relationship in the population. The types of things that we estimate in path models are paths, that's the easy one, variance of our exogenous variables. So exogenous meaning that causes are external to the model. So i.e. purely predictor variables, right? Error or residual variance. So how much variance in job satisfaction did we not account for? And then any covariances. So relationships amongst exogenous variables that aren't paths, okay? Now, let's go through each of these because it's kind of a doozy. How many paths do we have? This one's easy. Great, 5, yay, we can count. We can all count arrows, 5 paths. How many exogenous variables do we have, right? 5, right? We've got work passion, this moderator term, job variety, job autonomy, right? Those don't have anything predicting it. Their causes are external to the model, meaning we're not going to get variance explained in them, right? We're just going to get their variances. We're going to say, hey, out in the population, this is the spread of work passion. This is the spread of your moderator. This is the spread of job variety. So we've got how many variances to estimate? 5, 1 for each exogenous variable. How many error or residual variances do we have?
1.
What's a residual variance?
Very nicely.
Variance not explained, right? How many variables are we explaining variance for in this model? 1, right? So these 5 predictors are predicting job satisfaction. That's going to explain some chunk of the spread in job satisfaction. And whatever's left over is the error, right? So if we wanted to draw it in, which we don't always draw in, right? We would draw it here, right? Error. So job satisfaction is either explained by these 5 predictors or not explained. So how many error terms do we have? 1. Now, here's where it gets tricky. Covariances. So a covariance is a dual relationship between 2 exogenous variables, right? Not a path. So, for example, in the original model that you got drawn, this is a covariance, right? That relationship between job variety and job autonomy. It's just acknowledging that, hey, these might move together in some way. Why does that make sense? Well, they're both predicting the same thing, right? So if they predict the same thing, they should have some relationship with each other. But it's not a causal relationship that we're interested in. So we set it as a covariance. But here's the kicker. Anytime you're predicting an outcome from a bunch of exogenous variables, they should all have some relationship with each other. Or if they do, you want to be able to capture that in your model. So Levon has an automatic feature, which is that you don't have to specify those curved arrows. Levon is going to automatically allow all of your exogenous variables to correlate. If you don't, your fit is going to suffer. But what does that mean now? That means we have a lot of covariances, right? We have work passion to this moderator, work passion to this moderator, work passion to job variety, and work passion to job autonomy. Then we've got this moderator to the next one, and this moderator to variety, and this moderator to job autonomy. Anyone do the math? How many do we have total? Say it again. 10. Total those up, my friends. How many parameters are we estimating? 21. Uh-oh. What does that mean about our model? Just identified, right? We are estimating the exact same number of pieces of information that we have. Guess what? Regular regressions will always be just identified. That's why we don't run model fit statistics on regressions, and we run them with R-squareds only, right? We could have, from the very first day I taught you regression, run them in the Levon code, right? But every time we run a regression, all of those fit statistics that I just taught you for Path would be NA, because plain regression models are always just identified. You always have just the right amount of information for the parameters that you are estimating. Why we don't talk about that in regression. It's always going to be 0. What's the issue? What's the problem here? We're not going to get model fit statistics, right? If you just went and ran this in your DA and was like, why didn't I get model fit statistics? This is where you should go back to. If you're not getting model fit statistics and it says degrees of freedom 0, that's telling you that the amount of information you have is equal to the amount of things you're trying to ask R for. Okay? Yeah.
So when we are calculating the number of parameters.
Can you talk louder so people can hear
Oh,
you?
I remember when we last lecture, when we calculated the number of parameters, you used a theoretical model rather than the statistical model here, because during that mapping.
Oh, it doesn't matter. As long as you accurately count. It
So like
does.
even with the theoretical model.
Yeah.
But like I thought in the theoretical model, there was only like one covariation.
No, because actually, yeah, so the issue is in your theoretical model, right? There's one drawn here, but we know from R's automatic covariance that work passion is going to be allowed to covary with variety, and work passion is allowed to be covary with job autonomy. And actually, this is going to be a moderator term in addition, so both those moderators are also allowed to covary.
Okay.
Yeah, we would just have to count them, like, to know that from the theoretical model, which is why I put it here before we ran it. Now, there is an option in Levon, you can fix anything that you want, right? Meaning if you wanted to say work passion and job variety are not related, don't let them covary. Cool, just put a 0 in front of it. Why would I do that though? It doesn't make any theoretical sense. Clearly they all covary. I made moderator terms out of them, right? They're all related in some way. So we have no model fit. Let's look at what that looks like. So I'm gonna detect my processors, and then here's my model specification. I've got job satisfaction regressed onto my 5 predictors. JV, JA, work passion, first moderator term, second moderator term. And then what did I do here? Take a second and look. What did I do here? Take a second. This is like a critical thinking. What did I do? It's not like a you should just know looking. What did I do?
Simple path.
Yeah, I just asked for the simple slopes, right? One of the cool things about Levon is because it's all manual, you can use it as a calculator for yourself in any way that you want, right? So I said, I've got this moderating term here. So I want to know the relationship between variety and satisfaction when work passion is high, average, and low. I also want to know the relationship between autonomy and satisfaction when work is high, average, or low. So I said, just give those slopes to me, right? I said, when the moderator is average, that's like 0. So it's just gonna be JV to job satisfaction, as if the moderator doesn't exist. And then when the moderator is low, it's gonna be minus the moderator. And when the moderator is high, it's gonna be plus the moderator, right? Just like moderation code. This is another reason why standardizing first is really helpful, because now I've just done 1 standard deviation above and 1 standard deviation below. And I've done it from JV, and I also did it for JA. Then I'm gonna run it. I'm gonna use MLR. I don't have to use MLR because the data were normal, but I'm going to, because if it's normal, it won't matter. It'll be the same solution. I'm gonna run a summary, and then I'm gonna standardize everything, even though I don't really need to do that either, because it's all standardized. All right, let's start with model fit. Model test user model. That's your model. It's got no chi-square and no degrees of freedom. Why? It's just identified, right? We have 21 pieces of information. We're estimating 21 things. So we don't get a chi-square. If we don't get a chi-square, we don't get anything else, right? It will give you BS, CFI, and TLI. Don't be like, yay, it fits. It doesn't. It's automatic. No CFI robust. Those are your actual ones. No TLI, no SCA, no SR. So you just can't report model fit here, right? You have to say, because the model was just identified, right? Model fit indices are not available. However, what can we look at? No, y'all, it's a regression. What are we gonna look at? We can just look at the parameters themselves, right? And see, do these 5 things predict job satisfaction? We still get the parameters. We just don't get the fancy fit indices that go with structural models. Just like when we ran every other regression, we don't use the fancy fit indices for those models. So let's go down to the parameters. Why did it wrap it? That's super annoying. Let's look at the pretty one like this. Here are all of our parameters. So remember, we gave it names, so that helps us figure out what path does this belong to. Does job variety predict job satisfaction? Yes, right? Beta 0.14. Do we use p-values or confidence intervals here? Careful, think. P-values, right? We estimated this not with bootstrapping, right? Yes, you should report confidence intervals also, but the p-values are valid here, right? We just use robust maximum likelihood, right? These Z's are real. That's how we figured out whether something was significant, right? This beta, the beta of 0.14 is 2.5 standard deviations away from a beta of 0. That's what that Z means. How about job autonomy? Does that predict?
Yes.
Yep. How about work passion?
Yeah.
Yep. How about either of our moderators? No. Let's put that on our diagram. It looks like this, right? Why did I move back to the arrows like this? Because it's way easier for my brain to wrap my head around actual moderating on paths versus like the statistical layout. So what do we find in this model? Can't have model fit, but work passion, job variety, and job autonomy all predict satisfaction. Work passion does not moderate, right? We can also, you see this? .js, what is that? Error variance. Good, right? What does that mean? It means variance not explained. So 71% of the variance is not explained. So what's our R squared? 29, right? 0.29. So 29, so this model explained 29% of the variance in job satisfaction. We can report that. It's just a regression. That's our best fit stat that we have. All right, so here's our first model. What do we want to do? Now we get to respecify, right? First of all, how would we report this, right? We would start by saying we use path analysis to investigate the relationships between work characteristics and job satisfaction. Prior to specification, what did we do? That's a great phrase. We did a bunch of stuff prior to specification. What did we do? We checked all of our assumptions. We're going to say what they are. We're going to say whether they were satisfied or not, and we're going to provide the statistical evidence. What else did we do? We standardized our data. We're going to say that, right? What else did we do? Look at the code. We did one more thing. Yeah, right? Look, literally when you're reporting your prior to specification, go through your code, right? The first thing we did was examine descriptives, see table 1, and correlations, see table 2. Then we checked the following assumptions. Linearity, scatter plots looked good. Homoscedasticity, data was homoscedastic, confirmed by the NCV-Pagan test. Data were normal, confirmed by both a QQ plot and a Hunt circler. Then, what's what do? We standardized and created moderator terms. Just go chronologically through everything you did in your analysis and put it in your write-up. Okay, we're skipping like, oh, you did stuff, but you're not talking about doing stuff. Yeah.
Because this is kind of regular regression, would you say that you also have to report multicollinearity? Because I know that.
Yeah, you should probably check multicollinearity, but the two were, you could do it with correlations, or you could actually run a collinearity function if you wanted. And it's not because it's like regression, it's because it's general linear model. So even in a path model, you would do that too. So we standardized. Prior to specification, we also standardized and created moderator terms. Then what did we do? Literally, don't worry about that. What did we do? We specified model 1. We're going to explain what that is. And then what did we do after we specified it? What did we do in line 117? What comes after specify? Estimate. Good, right? So we specified a model, we fit it to the data, and estimated model parameters. How did we estimate? What did we use as an estimator? Robust maximum likelihood. That should be in your write-up, right? Model 1 looked like this. We then estimated parameters using robust maximum likelihood. Then what's the first thing we usually report? Model fit. Can we report model fit here? We can report the R squared, but we have to say, because our model was just identified, right? The indices were not available. However, the model explained 29% of the variance in job satisfaction. Then what do? What did we do next? What did we do next? After we said, oh shit, no fit. What did we do? Don't overthink this. Let's look at our model again. Oh, look, it popped up. Oh shit, no model fit. It's just identified. Better say that in my write-up. Then what did I look at? Yeah, I looked at my parameters next, right? A lot of you are thinking, what do I need to put in my write-up versus what did I do as a statistician? Just go chronologically through what you did as a statistician. That's your write-up. There's no you don't need to be wildly creative or clever in your results section. Do that in your discussion, right? So there was no model fit because the model was just identified. So we proceeded to look at our model parameters, right? Job variety, job autonomy, and work passion all significantly predicted job satisfaction. Stats. However, work passion did not moderate the relationship, right, between job variety and satisfaction or between job autonomy and satisfaction. See table X, whatever, for all model parameters. Good? Now what do we do next? What do we want to do next? Respecify, right? So just say that. We then proceeded to specify a second model. Model 2. This model had job variety and job autonomy once again predicting job satisfaction, but we also used job satisfaction as a predictor for turnover intentions and moderated that relationship with work passion. I'm literally just describing what I'm doing. Now, that's the model I specified. What comes after specification? Estimating. What's different about this model that's going to change my estimation technique? 2 outcomes, but that doesn't change my estimation. There's a relationship in here that requires a different type of estimation, right? I have 2 mediations in here. Job variety to satisfaction to turnover and job autonomy to satisfaction to turnover, which means I'm going to what? Bootstrap. So we specified model 2. I just described it. We then estimated model fit and parameters using bootstrapping to account for mediation analysis, right? So let's look at how I specified this in R. Oh, by the way, let's look back at this last one. The moderation was not significant, right? Check these out. Here is the moderation when work passion is low, 0.19, 0.14, 0.09. If we slope them, they look like this. They're actually all the same. And if we plot the other one, they're even closer. Right? Neither moderation was significant. So let's go to our second model. Do I have work passion times job satisfaction in my model? No, right? It was moderating the first paths before. So I need to create that moderator term. So here it is. And then I'm going to specify my model. So now I have a true path model, right? I've got multiple outcomes. So on to turnover intentions. I've got job satisfaction, work passion, and the moderator, right? So job satisfaction, work passion straight to turnover, and the moderator term. Then to job satisfaction, I just have job variety and job autonomy. We good with this part? Then I did the same thing where I was like, hey, go ahead and give me the relationship between job satisfaction and turnover. That's what I named the path. When the moderator is 1 standard deviation below, when the moderator doesn't exist, i.e. it's 0, and when the moderator is 1 standard deviation above. That's just to give me those simple slopes. Now, whenever I have mediation, what else do I want? Indirect effects. How many indirect effects do I have here? 2, right? The effect of job variety on turnover intentions mediated by job satisfaction, and the effect of job autonomy on turnover intentions mediated by job satisfaction. Let's do that. So here's job autonomy to job satisfaction to turnover, which is the first path, job autonomy to satisfaction. That's my A path, right? Times my B path, job satisfaction to turnover. Yeah.
Why don't you go with direct for the key path?
Because I didn't re-specify that way. I could, it would probably make the model fit better. Yeah, go ahead, let's add it. I don't want to do it yet because it's going to change all my parameters, but we can look at it, see if it fits better. So we have our indirect effects, and then this is like pushing the envelope on hard, but I want you to know it if you see it. Is it just job variety to satisfaction to turnover? What's also happening in that mix? Work passion is changing the B path, right? That's what we call a conditional indirect effect. It's an indirect effect that gets moderated somehow. Guess what? We can calculate that too, right? I know you can handle it, right? So basically we can calculate this indirect effect when work passion is low, work passion is average, and work passion is high. It's not new. I'm just asking you to put together a lot of shit that you know. None of it's new, but it does, the volume gets bigger. So how do we do that? Well, we know how to put together the indirect effect. That's just variety to satisfaction to turnover intentions. Well, when work passion is high, this relationship is going to change by the moderator. So we can combine those together. So let's start with variety because I just talked about that. So when work passion is low, it's going to be the first path, which is A, that never changes. There's no moderation on it, times our B path, which we created up here, right? Up here, we said, what is the relationship between job satisfaction and turnover going to be when work passion is low, work passion is average, and work passion is high? We can just do that down here. We can use that predetermined parameter. Then we're going to estimate the model. We're going to use bootstrapping because we've got mediation, okay? And now we have model fit, right? We have model fit because now we have more pieces of information than parameters we're estimating. So we have chi-square 31.56. We've got a TLI of 0.72 and a CFI of 0.87. Not great. We've got an RMSEA of 0.15 and an SRMR of 0.06. Overall, with the exception of this fit statistic, none of them meet the threshold, right? So again, model 2 delivered mediocre fit. With the exception of SRMR equals 0.06, none of the other fit indices met guidelines specified by Schreiber 2017. See table whatever for fit statistics. We can look at the parameters again to see what worked and what didn't. I'm going to jump us to that. So here's the model fit, right? Chi-square is the difference between your matrix and the observed matrix, specified, right? Expected versus observed. But it's the cumulative difference. It's all the differences added together. Then we've got TLI and CFI. This is how much better your model is than the null. And then we have RMSA and SRMR, which are both the error, the standardized error between your model matrix and the observed matrix. None of these are great with the exception of SRMR is fine. So we would say that. Now we can look at our individual model parameters to see what might be the source of the misfit. So one thing here is that work passion does not moderate this relationship either. But Emily had another really great suggestion for fit, which is what? What did I not specify in this model? I didn't specify the direct effects from job variety to turnover or job autonomy to turnover. Let's put those in and see what happens to our fit. 24.82 degrees of freedom 2. CFI went up, TLI went down. RMSE did not get better. SRMR about the same, right? That tells me that one of those direct paths was not actually significant, right? It didn't help my model fit at all. then we've got our indirect effects, and then there are those conditional indirect effects. Look at these conditional indirect effects for a second, right? Negative 0.21, negative 0.21, negative 0.22. Why are they all the same, basically? Because there's no moderation, right? That work passion was not significant. It's only changing this path by basically nothing, right? So regardless of whether work passion is low, average, or high, the indirect effects aren't really changing. If work passion moderated that path, then those conditional indirect effects would change.